Welcome back to AI.Code.Cast. Today, we're going to dive deep into a classic coding problem.
Yeah.
Finding the median of two sorted arrays.
This is a fun one.
Yeah, this one's a favorite in technical interviews.
Oh, yeah, fun.
And it's trickier than it sounds.
Yeah, it's definitely trickier than it sounds.
Like at first, you're like, oh, two lists of numbers already sorted. Find the middle value if you combine them. Like, that sounds pretty easy.
Yeah, it sounds deceptively simple.
Yeah, deceptively simple.
The sorted part is key.
Right.
That's really where the efficiency challenges come in.
Yeah.
And the clever solutions.
So like imagine you're dealing with two data sets, right? So like sensor readings or stock prices over time, and they're each sorted.
Yeah.
But you need that overall median value.
Right, exactly. And I mean, the brute force approach is just to merge the two arrays and then sort the whole thing.
Yeah, but that's not very efficient.
No, especially when you're dealing with massive data sets.
Right.
Sorting a huge merged array can be a real-time sink.
Yeah. So how do we avoid that?
Well, there are a few ways.
Yeah, our research pointed to three main approaches that we can use that are more efficient.
Yeah.
Two pointers, binary search,
Yeah.
and a supercharged binary search.
Yes. Each with its own trade-offs between simplicity and performance.
So let's start with two pointers.
Sure.
What's the intuition behind this approach?
So it's kind of like we're simulating a merge sort, but we're taking a shortcut. Instead of actually merging and sorting the entire combined array, we just use two pointers to walk through the arrays, comparing elements as we go.
So like two fingers running along the list, pointing at the next element to compare.
Exactly. And we move the pointer that's pointing to the smaller value forward, so we're effectively merging the lists on the fly.
Oh, interesting. And how do we actually use those pointers to find the median?
So we keep track of how many elements we've processed, right? Because to find the median, we need to reach the middle position of the combined array.
Right. So once we've processed enough elements to reach the middle, we've found our median.
Almost. If the combined array has an odd number of elements, the last element we processed is the median.
Yep.
If it's even, we need to average the last two elements we processed.
Okay, that makes sense. Could you walk me through a simple example just to solidify this concept?
Yeah, for sure.
But with small arrays or something?
Let's say we have two small arrays. We have 1, 3, and 2.
So the combined array would be 1, 2, 3. So the median would be 2?
Right. And with the two pointers method, we start with a pointer at the beginning of each array. We compare the first elements 1 and 2.
Okay.
1 is smaller, so we move the pointer in the first array forward.
Got it. So now we're comparing 3 and 2.
Exactly. 2 is smaller, so we move the pointer in the second array forward. And since we've now processed two elements, which is half the total number of elements, we know we've reached the median position.
And since the combined array has an odd number of elements, the last element we processed, which is 2, is our median.
Exactly.
I'm starting to see how this works.
Yeah, it's all about efficiently finding the elements that would be in the middle if the arrays were merged without actually doing the full merge and sort.
That's clever.
Yeah.
It seems like this would be pretty efficient, especially compared to brute force sorting.
Yeah. The time complexity is O(m) plus n, where m and n are the sizes of the arrays.
All right.
This means that the time it takes grows linearly with the size of the input.
Okay, so if the arrays double in size, the time it takes roughly doubles as well. That's much better than sorting, which has a time complexity of O(n) log n.
Precisely. And the two pointers method only uses a constant amount of extra space, so it's very memory efficient.
Okay, so two pointers, intuitive efficient and memory friendly.
Uh-huh.
But I suspect there are some trade-offs, like when might this method not be the best choice?
Yeah, you're right. The main limitation is that it only works for sorted input arrays. If the arrays were unsorted, this method wouldn't be efficient at all.
That makes sense.
Okay.
Okay, so we've got a good grasp of the two pointers method. Now let's move on to something a bit more mysterious, binary search.
Yes, binary search, a classic.
Yeah, and often a bit intimidating at first glance.
Right.
Yeah, it's always felt a bit like magically how it can find things so quickly.
Yeah.
But how do we apply it to this problem of finding the median of two sorted arrays?
So the key is to shift our thinking a little bit. Instead of directly searching for the median value, we can use binary search to find the derth smallest element in the combined array, where der relates to the median position.
Hold on. Finding the nth smallest element.
Yeah.
How does that help us find the median?
So think about it. If we know the total number of elements in the combined array, we can calculate the position of the median, and that position is essentially the nth smallest element.
Ah, I see. So if the combined array has 5 elements, The median is the third smallest element.
Exactly. And if it has 6 elements, the median is the average of the third and fourth smallest elements.
Okay.
So by finding the appropriate path smallest element, we can either directly get the median or the values needed to calculate it.
Okay. I'm starting to see the connection, but how do we actually apply binary search to two arrays? It's
Right.
usually used to search within a single sorted array.
Right. So that's where things get interesting. We need to adapt the concept of binary search to work across 2 arrays. Instead of having the search space within a single array, we'll be strategically discarding portions of one or both arrays based on comparisons.
Okay, I'm intrigued. Walk me through how this works. We're aiming to find the nartheth smallest element.
Yep.
And we're doing this by comparing elements from the two arrays and discarding portions.
Exactly. And we do this recursively. We'll keep narrowing down the search space until we pinpoint the northest smallest element.
So it's like we're performing a binary search to find the right split point between the two arrays that will ultimately lead us to the median.
We want to divide the combined elements into 2 halves, where the largest element on the left side is less than or equal to the smallest element on the right side.
Oh, that makes sense. That's how we isolate the median or the elements we need to calculate it. Okay, this is starting to make sense, but what's the advantage of using binary search here? Is it really more efficient than two pointers?
It is especially for larger data sets. Binary search has a time complexity of log plus n. And remember, logarithms grow much more slowly than linear functions.
So as our arrays get bigger, binary search starts to really outperform the two pointers method.
Exactly.
But we mentioned recursion. Is there a potential downside to using a recursive approach like this?
You're sharp.
Yeah.
Yeah. Recursive algorithms can sometimes lead to Stack Overflow errors if the recursion goes too deep.
Oh, right.
This is something to keep in mind, especially if we're dealing with extremely large arrays.
Okay, so binary search is powerful,
Yeah.
but comes with a caveat, a trade-off between speed and potential memory issues. Fascinating. Now, you mentioned a supercharged version of binary search. I can't wait to hear what that's all about.
That's where things get really clever. We'll explore that next, along with a deep dive into how it optimizes the binary search approach even further.
Okay, listeners, stay tuned. We'll be right back with more on how to crack this median finding challenge with even more efficient algorithms.
Welcome back to AI.Code.Cast. Before the break, we were really starting to get into the weeds of binary search and how it applies to finding the median of 2 sorted arrays.
It's a bit mind-bending, I'll be honest, but I think I'm starting to wrap my head around it. Like, we're essentially using binary search to find the NASA's smallest element,
Right.
which helps us pinpoint the median.
Exactly. And remember, we're adapting binary search to work across 2 arrays,
Right.
which adds a whole other layer of complexity, right? We're not just looking within one array, we're strategically dividing and conquering
Yeah.
across both arrays.
Right, we're trying to find that perfect split point
Yes.
where the largest element on the left is less than or equal to the smallest element on the right.
Exactly.
But I'm still a bit fuzzy on how we actually do that with binary search.
Okay, so let's break it down step by step.
Okay.
So first, let's visualize these 2 sorted arrays, A and B.
Okay.
Our goal is to find a partition in each array.
Okay.
Let's call them partition A and partition B, such that all the elements to the left of partition A and partition B are smaller than all the elements to the right.
Okay, so partition A and partition B are like dividing lines within each array.
Yes.
And we're trying to find the right places to put those lines so that they create a median split across both arrays.
You got it.
Okay.
Now here's where binary search comes in. We're going to perform binary search on one of the arrays, let's say array A,
Okay.
to find the right position for partition A.
So we start by looking at the middle element of array A.
Right.
How do we decide if partition A should be to the left or to the right of that middle element?
So we need to consider the corresponding partition in array. B, remember the total number of elements on the left side of both partitions should be roughly half the total number of elements in both arrays.
So if partition A is at a certain position, we can calculate partition B based on the total number of elements we need on the left side.
Exactly.
Okay.
Once we have a potential partition A and its corresponding partition B, we need to check if they create a valid median split.
Okay, how do we do that?
So to do this, we look at the elements at the boundaries of these partitions.
Boundaries, what do you mean?
I mean, the elements right next to the partitions, we need to compare the maximum element on the left side of partition A with the minimum element on the right side of partition B,
Okay.
and vice versa. We compare the maximum element on the left side of partition B with the minimum element on the right side of partition A.
Okay, I'm visualizing those 4 elements, the max on the left and middle on the right of each partition.
Right.
So what are we looking for in these comparisons?
We want to make sure that all elements on the left are smaller than all elements on the right.
Okay.
If the maximum element on the left side of one partition is greater than the minimum element on the right side of the other partition, we know we have a problem.
It means our partitions aren't in the right place.
Exactly.
So how do we adjust them?
That's where the binary search logic comes in. If we find that the left side is too big, meaning an element on the left is greater than an element on the right, we know we need to move partition A to the left.
To shrink the left side
Yeah.
and make the right side bigger.
Precisely. And if the right side is too big, meaning an element on the right is smaller than an element on the left, we move partition A to the right.
So we keep adjusting partition A using binary search,
Yeah.
calculating the corresponding partition B,
Right.
and checking those boundary elements until we find the sweet spot where all the elements on the left are smaller than all the elements on the right.
That's the idea.
Okay.
Once we find those correct partitions, we can easily calculate the median.
Okay. This is starting to click. It's like we're playing a higher or lower guessing game with partition A,
Uh-huh.
using those boundary comparisons to guide our search until we find the right split.
That's a great analogy.
Oh,
Now, even though this binary search approach is more efficient than the two-pointers method, especially for large arrays, there's a way to optimize it even further.
oh, you're talking about the supercharged binary search we mentioned earlier.
Yes.
What's the secret sauce?
The key insight is that we don't have to perform binary search on the larger of the two arrays. We can just focus on the smaller one.
Wait, why would we do that? Wouldn't searching through the smaller array limit our options or something?
Not at all. Remember, we're ultimately trying to find the right partitions in both arrays.
Right.
And the positions of these partitions are related by performing binary search on the small array. We're essentially optimizing the process of finding those related partitions.
Okay. I'm curious, how does focusing on the smaller array make things faster? And how do we even implement binary search on just one array when we need to consider both?
Those are great questions, and we'll dive into those details after a quick break. When we come back, we'll unpack this smarter binary search approach and see how it takes efficiency to the next level.
Welcome back to AI.Code.Cast. Before the break, we were talking about focusing on the smaller array for binary search.
Right. It's a bit counterintuitive, but it can make a big difference.
Yeah, I'm still trying to wrap my head around why it matters which array we choose for our binary search.
Okay, think of it this way. Imagine you have two stacks of papers, one much taller than the other. You need to find the middle document. If you combine the stacks, would you rather search through the giant stack or the smaller one?
The smaller one, of course.
Exactly. It's the same principle with our arrays. Binary search is all about having the search space with each step. So if we focus on the smaller array, we're dealing with a smaller search space from the start.
Ah, that makes sense. It's like we're taking a shortcut by using the smaller array as our guide. But how does this actually work in practice? We still need to consider both arrays when finding the median.
Right, we're not ignoring the larger array, we're just using the smaller one to drive our binary search process. Let's say array A is the smaller one. We'll perform binary search on A to find a partition. Partition A. Just like we did before, we'll compare elements at the boundaries of the partitions to see if they create a valid median split.
So we'll still need to calculate the corresponding partition B in the larger array based on partition A and this whole number of elements. And then we'll compare those four boundary elements, max left, A min right, A max left, B min right.
Precisely.
Hmm.
If the boundary conditions aren't met, meaning an element on the left is greater than an element on the right, we adjust partition A using binary search, recalculate partition B, and repeat the process.
So the logic is the same as before, we're just applying it to the smaller array. It's like we're delegating the heavy lifting of binary search to the smaller, more manageable array. I bet this saves a lot of time, especially when the size difference between the arrays is significant.
You're absolutely right. By focusing on the smaller array, we reduce the time complexity to O log m in n, where min mn represents the size of the smaller array.
So instead of having the combined size with each step, we're having the size of the smaller array.
That's brilliant.
But doesn't this make the implementation more complex? It seems like we're adding an extra step to figure out which array is smaller.
It's a valid concern, but the added complexity is minimal, and the performance gains can be significant, especially for large datasets, where one array is much smaller than the other. The space complexity is still O1, so it's very memory efficient.
So it's a trade-off.
Yeah.
A bit more complexity in the code for a potentially big boost in speed. It sounds like this smarter binary search is a winner if performance is a top priority.
Exactly. It's all about choosing the right tool for the job. If you're dealing with massive datasets and need the fastest possible solution, this approach is hard to beat.
Okay, we've covered three powerful methods for finding the median of two sorted arrays: two pointers, binary search, and this smarter binary search. It's amazing how a seemingly simple problem can lead to such clever and diverse solutions.
It really is. It speaks to the power of algorithms and the different ways we can approach problem solving.
I love how this deep dive has highlighted the importance of understanding time complexity and choosing the right algorithm based on the specific requirements of the problem.
Absolutely. And sometimes the most efficient solution isn't always the most obvious one. It often requires thinking outside the box and challenging our assumptions.
Well said. So listeners, if you ever find yourself facing this classic coding challenge, remember the three approaches we've discussed today. Two pointers for its simplicity, binary search for its efficiency, and smarter binary search for those times when speed is paramount.
And don't be afraid to experiment and explore different approaches. The process of problem solving is just as valuable as the solution itself.
Thanks for joining us on AI.Code.Cast for another deep dive into the world of algorithms. Until next time, happy coding.